Welcome! Today we'll take a brief look at continued fractions and get a taste of the art of recursive thinking. We'll explore how numbers can tell their own story through self-similarity. Traditional math treats a fraction as a fixed destination. The numerator and denominator are resolved, resulting in a finite story with an exact value. What if we refuse to let the denominator be a static number? We can start with a simple fraction, like 1/2, and continually replace its denominator with a new expression, building a mathematical echo. By repeating the replacement process, a pattern begins to take shape. Each step involves substituting a complex fraction for a simple number, leading to an endlessly nested structure. But where is this going? Tracking the resulting fractions reveals a pattern of Fibonacci numbers. Each new numerator and denominator is built from the two steps before it. Macrostructures emerge from microsimilarities. In this example, we started with 1/2. The values of these fractions converge toward a specific threshold. While they bounce above and below the target, the infinite process eventually settles, approaching a very specific limit. If this process never stops, the inner part of the fraction has the exact same shape as the whole expression. This infinite fraction becomes a self-referential equation, where the part is the whole. Solving the self-referential equation reveals the value. This simple recursive game with 1/2 secretly builds the inverse of the golden ratio, one of the universe's most famous numbers, approximately 0.618. Of course, other numbers would have emerged if we started with a different fraction such as 1/3 or 1/4. Can continued fractions tame an irrational number like the square root of 2? We must first isolate the integer part from the infinitely messy fractional part to begin the recursion. The conjugate acts as a mathematical filter, turning the chaotic decimal part into a clean reciprocal form. This allows us to rewrite the number without changing its value, setting up the recursion. The recursive door opens, allowing us to endlessly replace the inner square root of 2 with its expanded form. This continuation process creates the infinite nested fraction. The number 2 repeats endlessly in the square root of 2 continued fraction, because the integer parts combine. This leaves the fraction to echo forward indefinitely, creating a permanent 2. Comparing static and recursive math shows two different lenses on reality. Traditional math seeks a final, exact value, while recursive math seeks an underlying, self-similar pattern in an infinite, open nature. By computing the first few steps of different continued fractions, you can observe the echo and predict where they might converge. Do they grow, shrink, or bounce and settle? Recursion teaches us that colossal, infinite macrostructures can be built from simple microsimilarities repeating themselves. A continued fraction is a story about a number asking what is inside of me. Thank you for watching. When you have time, please grab a pen and play with some continued fractions. They are really fun and shed light on the power of algebraic and recursive reasoning. Until next time.